In this question, we've been presented with an unidentified compound, and we've been told that it contains barium, iron, and oxygen, and we've been asked to work out the empirical formula for this compound. Okay, so one of the first things I'm going to do, we've been given the percentage, effectively the percentage abundances by mass of each of the elements in the sample. I'm going to actually add up those percentages just to check what the total is. So if I do that, 43.88 plus 35.67 plus 20.45, and if I do that, I get 100, right? So I would I recommend, try out for yourself, see what you get, but if you do that, you're going to get 100, right? Okay, now in order to solve for what's been asked, the empirical formula, I'm going to make an assumption, which is I'm going to assume that the masses or the total mass of the unidentified compound is 100 grams, right? And as you can see from this calculation, if we do make that assumption, this has some implications for the masses of the constituent elements that make up this compound. So in this case, for barium, this would mean that the mass of barium in the compound is 43.88 grams, right? And then for iron, similarly, this would therefore be 35.67 grams, and for oxygen, right, it would be 20.45 grams. And let me just put the element symbols here. So barium, Ba, iron, Fe, oxygen, O, right? So, but at this stage we've got masses, and because we know that with each of these elements they've got different relative atomic masses, it's not easy to directly compare the actual specific amount of substance, the amount of atoms of each element present in the sample relative to each other just using a mass, right? And because of that, I'm going to use the relationship between mass and moles, which, as we would know, that the mass is equal to the moles, which you represent by N, multiplied by the molar mass mR, right? And in other words, if we rearrange this, if we divide both sides by the molar mass to make the moles the subject, we understand that the moles N is equal to the mass in grams divided by the molar mass mR in grams per mole, right? Okay, so considering this, we are now going to take a look at converting these values into effectively molar quantities, and we're going to establish a ratio between them in terms of amount of substance. In order to do that, as you can see from the equation, what we do need is the molar masses of each of these elements, and well, we can get that simply by getting the relative atomic masses from the periodic table, which is what we're going to effectively do at this stage. So as you can see here, barium, iron, oxygen, right? So I mean, I've grouped them over here, but you can see them also as part of the, what is this? Yeah, so you can see it as part of the periodic table anyway. So barium, iron, oxygen, right? So I'm gonna do just quickly write out the molar masses here. So for barium, so put this MR of barium, just do it like that. That's gonna be 137.3. MR of iron, that's gonna be 55.8. and MR of oxygen, it's going to be 16, right? Just says 16 point, but 16, right? Okay, so at this stage, as we know from the equation, all we simply need to do is take these molar masses and use them to basically we need to divide the masses by their respective molar masses. So divided by 137.3. Iron, we're going to divide that by 55.8, and oxygen, we're going to divide that by 16, right? Right, so at this stage, I would invite you to have a go, try and see if you can work those out, and just see what you get. Okay, so BAFEO, right? And when you do that, what you should get in the case of BA, so now we're kind of at the stage of establishing somewhat of a ratio. So 0.31959, and for iron, if you work that out, you should get 0.63925, and for oxygen, should get 1.27813. Okay. Now our target, as we know, our target is we're trying to work out the empirical formula. Now all of these numbers at the moment, you can see you've got a lot of well, none of them are a whole number, which is an issue if we're trying to work out the empirical formula. We were aiming to get the simplest whole number ratio, right? Clearly what we have here is not the simplest whole number ratios, but at this stage, in order to get at least one of these values to be a whole number, what we're going to do is simply divide every single one of these values by the smallest value, right? So in this case, the smallest value, as you can see, is that of the molar quantity that we've attributed to barium, the 0.31959. So if we do that at this stage, so let me just I would invite you to have a go, try and work that out. So 0. Right, and if you run those calculations, so in this case, you don't need a calculator to work that out. That's just going to give you 1, right? Because you're dividing this by itself. Now, in the case of the others, okay, so in this case, in the case of iron, you're going to get 2.00022, and in the case of oxygen, you're going to get 3.99928. Okay, so at this stage, if we consider, well, when we look at all of these values we have now, Of course, some of them appear to still have some decimals, but all of them are incredibly close to a whole number. Of course, the one associated with barium is a whole number, but the other two are very, very, very close to being a whole number. I mean, if we round the value associated with oxygen to 3 decimal places, it's within effectively 0.001. It's like this close to a whole number, which is very, very close, right? So at this stage, if we take a look at considering, well, if these were all rounded to 2 decimal places, would we have all whole numbers, right? So of course this would be a whole number, but in this case, well, if you round this, yes, this is going to be 2, and if you round this, okay, yes, this is going to be 4, right? Based on that, we can now say that actually, you know what, we're going to just simply round these and look at what we get. So if we do that, 1, it's going to be 1 to 2. So at the moment I'm just rounding it to 2 decimal places, but as you can see, if we now ask ourselves, well, do we now have all whole numbers? And the answer is yes. Across the board we have whole numbers, and the follow-up question would be, well, is it our simplest whole number ratio? Now if this had said 2, 4, 8, right? If it had said 2, 4, 8, which it doesn't, but if it had said 2, 4, 8, of course we would say, well, no, it's not the simplest whole number ratio. You can divide it by 2 and get a set of other whole numbers. But in this case, yes, this is our simplest whole number ratio. And so therefore we can attribute to barium a 1, we can attribute to iron a 2, we can attribute to oxygen a 4, right? And of course in a actual formula we're not going to write a 1 here. That's not how we would represent it, but effectively we would have Ba Fe2 O4, and in this instance this is our empirical formula, okay? Ba Fe2 O4.